It's 9:05, so by MIT tradition, I guess we are good to get started. So good morning, everyone. Welcome to this student conference. Today, we are excited to have Professor Ne Li as our plenary speaker. Professor Ne Li is a Gordon McKay Professor in Electrical Engineering and Applied Mathematics at Harvard University. She received her Bachelor of Science degree in Mathematics from Zhejiang University in 2007 and PhD degree in Control and Dynamical Systems from California Institute of Technology in 2013. She was a postdoctoral associate at MIT from 2013 to 2014. Her research lies in the control, learning, and optimization of networked systems, including theory development, algorithm design, and applications to real-world cyber-physical societal systems. She received NSF Career Award in 2016, AFSOR Young Investigator Award in 2017, ONR Young Investigator Award in 2019, Donald P. Ackman Award in 2019, McDonald Mentoring Award in 2020, along with other awards. Please join us to welcome Professor Li.
Thank you, Bai, for the introduction, and thank you everyone for coming to the talk. So it's my great pleasure to come back to this and to share of my some recent work my group has been working on. That a very precious memory at least. So I hope you guys will give me feedback. So what's the future work of this direction? So before the talk, I would like to thank all my students and postdoc who are the main contributors to this work. And there are 3 students and postdoc me that actually on the job market. Yujie, Yinyin, and Xin, they are on the job market right now. And Yujie is the main player for all the work I'm going to talk about. And also Zhen Yang already started his assistant professorship at San Diego. If you guys have questions, feel free to email me or anyone from the author list. So let me give, since it's early in the morning, so I will start with a very high level of motivation to make it easy for the transition. So in the past decade, we have seen an explosion of data. So here I'm going to take in the photo as an example, the photography. So anyone know what's this picture? Give one few seconds to think about this image. So this image actually what I found online is actually the earliest photo that people have been our humans have ever taken. So which was taken at 1827. So since the first photograph, now you can see how much the growth of the photography in the past 200 years. So I would say the growth of the photography was pretty slow until the end of last century, once we have the digital camera, especially our cell phones. So then we see a boom in the number of photos. And here's a famous ImageNet, which is a big pusher for the machine learning methods. And this is actually a snapshot for my own cell phone. And you can see I took too many repetitive photos for my kids and I do not want to delete any of them, which actually can provide a good resource if people want to do pattern recognition about the face expression. So with the exposure of the photos, we have seen a revolutionary of learning method in the past decades, especially once deep learning has outperformed humans in image recognition, deep learning is almost everywhere. So besides the image data, there is an explosion of other types of data, for instance, the IoT data. So our society has more and more smart devices, which are capable of sensing, communication, and computation. So with this data and with this kind of devices, we start visualizing smart houses, smart manufacturing, smart transportation, and smart personalized healthcare. So those are beautiful picture about the future. Then we look at the progress. Indeed, there have been many exciting news. I think every year Boston Dynamics will post one cool video about how the Boston Dynamics robots had been performed very difficult task. This is about Atlas, right? Every time I watch the video about Atlas, I was imagining how am I able to do this? I don't think if people even train me hard, I'm able to do any backflip. But at the same time, if we just go ahead to Google it, we will also find the failure videos. So it's hard to imagine, right, how many experiments they've been doing, right, in order to collect enough data, or are they really using this kind of deep learning? At least right now, from the outsider, it's hard to know how they're really making the set of videos. So this is about like the robotics that probably in the future. So now when we look at, speaking of the societal system, that's actually closer to our daily life. The situation is actually even more cruel. Even like early last year, there was a big unexpected winter storm in Texas. To couple with the winter storm, ERCOT had to perform rolling blackout. So millions of people's life got affected, and there were like 246 deaths that reported that relate to this winter storm. So you can see like, even we have those kind of smart devices, but when there's a big urgency, winter storm comes, we kind of go back to some like old solutions. So now speaking of the autonomous driving, like, even though everyone is so excited about mixed autonomy, when we go ahead to watch those YouTube videos, it's devastating to watch the tragedy news of the car crashes. So the message is that like learning for physical, societal, dynamical system is very challenging. It's different from just learning the data from the image data or from the language data. So to address those challenges, there has been a growing need in integrate machine learning and dynamic control. Well, I would say in the past years, those like learning and control community has been kind of working together like for a long time. So now we look at like the current trend, right? So this is my biased viewpoint from a theoretical point of view. What's the difference between the two research area? So speaking of the learning, like learning is powerful in image recognition, language processing. And from the theory side, like a lot of people, when they develop the learning method, the question people ask is, hey, can I improve the query speed? Can I improve the sample complexity? If I'm doing the online learning, can I making sure the regret is not big? And if I like for the image recognition, like I really care about the generalization, like the statistical guarantee. And then speaking of the control, we have been control, like, and my background training is more from the control side. So every time we really think about the real physical system, right? This thing, first question always coming to our mind is like, how about stability? Can we making sure the system not going to crash? And then we talk about robustness, because there's no model is perfect model, right? How can we guarantee my controller is still going to work, even if the model is not really as clean as what we modeled in the lab? Like, what about the worst case assurance? And once we putting our system into a big system, do the integration, and the global system will still have certain performance. Right? Those kind of perspective every time we try to design the controller for physical system. So you can see for the application I was mentioning ahead, societal, physical, dynamical system, given the complexity of the system, it kind of makes sense, right? Can I use kind of learning to harness the data by the IoT devices? But then I also use the control tools to making sure my system can perform well no matter what the environment is. So there's a growing need to integrate them, but the difficult question is how? Like, it's not that natural. Like, what's the difficulty? How are we going to address those difficulties? So I'm going to narrow down the discussion to be more focused. So machine learning is a big field, control is a big field. So for today's talk, I'm going to only focusing on like very narrow perspective about the integrations through the zeroth order method. What do I mean by that? So give you some examples. First, let's look at like two typical machine learning problems. So the first problem is a supervised learning. So for the supervised learning, typical the problem is like I have a lot of data. And based on the data, I want to learn a model to do the prediction. So I would like my prediction is as close as the ground truth. So the metric is going to be loss function. So once I formalize the optimization problem, I go ahead using the optimization method, and typically it's a stochastic gradient and its variant are those popular methods people are using now. So now the other problem that's I think very popular these days is like I call here, I kind of using the keyword from the machine learning, like banded learning, or you call it the black box learning. So what that means, yeah, again, I would like to find the optimal decision, but the difficulty is the environment is so complex. So I took decision, but I do not know how to really model the J specifically. But what I can do is I can take in a decision theta, and I can observe the outcome, how my theta is really doing. So based on this black box like feedback, I've tried to improve in my decision making. So like there is, if you go to the discrete domain, you can like talk about Thompson sampling and upper confidence bound. Once you go to the continuous domain, especially when the J is smooth, then we can do some gradient estimator, like which is called zeroth order method. So those are kind of two examples of the machine learning. Now let's look at the standard control problem. So what the standard control problem is, I know for this community, probably all of you already took the control class before. Very quick introduction for the control, right? For the control, we always start with the dynamical system. So dynamical system has a state X, has a observation Y. And the system will have external disturbances, has noise in the measurement, and we observe our measurement. And what the control trying to do is to find the feedback control rule that's based on my observation. I will take the control action, I will to shape my system dynamics. And there are different kind of control questions. That's like if you took different control class, you will look at this kind of keyword, like how to find the controller to stabilize the system, how to design the controller to optimize, how we guarantee robustness through the edge to infinity. Like how can we really design my controller that's making sure my system can adapt to the external changing time environment. And Shimi Seeking talking about, hey, what if I even don't know my objective function, I don't know my f and h, can still like making sure my controller is doing a certain kind of job. So those are different kind of topics in the control field. Now let's look at the connection between them. First, if we talk about learning for control, this is one natural way and which I think both learning and control people have been working on for a long time, is first, based on the kind of supervised learning method, right, I'm going to find a model to do the prediction. So one natural way is I can using the learning method, which in the control we call it system identification, to identify the underlying dynamical system from the data that we have been connected. And once we have a model, even the model is not perfect, then we can go ahead to do the control synthesis. And when we do go ahead to do the control synthesis, like we can, one thing we need kind of making sure is that our model is not really accurate, right? How can we really taking care of this kind of uncertainties, the modeling errors? So this is kind of one way, like we can definitely using the learning to predict my model. So this is another perspective, but like the challenges for here, you can imagine. So first of all, if the system is not complex, if I already have a physical knowledge of the model, that's good, right? Then I know what kind of data I really need to learn. So I can use in the supervised learning, doing the optimization to estimate unknown parameter data. But if the system is very complex, so even not like some physical model start with, especially once you have the human in the loop, this is becoming difficult. First question, what kind of model are you going to pick? And then even though we have like say doing some model right now, some people putting the deep neural net to really model the dynamical system. But once you have that, the other question, control synthesis, actually can become very hard if we making our model too complex. Right, nonlinear control is challenging. We do not really have like many tools to handle all different kind of nonlinear dynamical system. So kind of the challenge for the model-based method. So now there's another method getting popular because at least I can just go ahead to like do some simulation, we'll get some solution. What's the other method? So let's look at the black box learning. So what I've been doing here is, so as I mentioned, like for many problems, it's actually hard to model the system. And so I'm not going to really model the system. I'm just kind of taking the system as a whole. So now what I'm doing is I will parameterize my control policies. Like I can go ahead, even make it as complex as possible, like using those deep neural net parameterization. So once I pick those parameters, so what's really for my feedback loop system is I can observe, like putting everything together, how good my controller is. And if we go ahead, we can put in mathematical formulation, say, hey, this is some reward or some cost just associated with this control parameter theta. In that sense, what we're going to do is like, hey, I can change my theta, and then run the simulation. I'll just put in the system into reality and observe for a certain time period. And I can try to guess how good my system is. So once I want to highlight this, there's lots of uncertainty stochastics happening in the system. Like every time when I try to evaluate the performance of the theta, it's always going to be affected by the external disturbances or some noises, right? So that's why I put in the J tilde, not really the J. It's impossible to have the true J by using the limited number of data or the limited number of channels. So now the challenge for this one, right? Hey, this looks like I can go ahead to test the algorithm, but what is the performance, stability, probability, convergence? Like how many times you really need to run those simulations? And another big challenge for this problem is it's kind of really totally throw away my prior knowledge. But what if I have some knowledge of my system? And how to incorporate this prior knowledge? But those are the challenges of those problems. So I'm not going to give you an answer for those, but I still have a question for like how to answer those questions. So I'm just going to show you some progress we have been doing in our group. So this is about like learning for control. Another thing I want to highlight is this. So even though I say those are learning for control, but in another perspective, you can also view those model-based and the model-free control method also as a control for learning. What do I mean by that? If I really want making my learning be useful for the physical system, I have to deal with this dynamical system questions, right? In order to making the learning be useful, I'm going to redesign the good learning-based control. You can also view those learning for control as control for learning, like how to make learning be useful. But there's another direct way of like control for learning. So that's what I'm going to talk about today. Is now come back to those learning methods. Right? There are different type of learning methods. But like for these two examples, like the supervised learning, people using the stochastic gradient descent are like it's borrowed. And for the bandit or black box learning, again, there's a different type of method. So no matter what type of method, all the method is iterative method. Like what iterative method means is, okay, I will take some like guess about my theta, like either which is my model, my optimizer, and I get more information either through the data samples, like I got a information like getting the bandit feedback. So I have this update, and then I go to update. So you look at this one, this actually looks like, I mean, not really looks like, it is a dynamical system. But this is the discrete time dynamical system. So once we recognize this is a dynamical system, what we can do? First, we can use our dynamical system knowledge to analyze the performance. Right? Besides the convergence rate, like those questions that already being asked by those optimization and learning community, we even can ask some other questions, right? What about the transient behavior? What about robustness for this learning algorithm? What if you have some computational error in this like learning loop, what will happen? That's what I mean by the analyzing. First, we can actually analyze additional performance, which are important for the practical application. So once we analyze the performance, then go ahead to ask, right, hey, can we even improve it? Right, there are methods that's to improve those methods from the learning perspective, but probably we can even use those control dynamical system tool to kind of shape the dynamics, like even to help the transient or even to help the robustness. So that's another perspective, like how control can be useful to helping developing, improving the learning method. So like, and actually there are a lot of work and a lot of success in this domain, especially I think around the natural method, because it's kind of a magic, like natural method performs so well, like what's really happening. So like if you guys are interested, and then all those papers are very, very nice papers to kind of center around the natural method to see how the dynamical system point of view can help it. So today's talk, as I'm not going to answer all the questions I raised. I will say all the questions were meaningful questions to do a PhD thesis. And like the talk, I'm going to focus on like two perspectives. So for the learning for control, I'm going to focus on the model-free part. So the model-free control, like I'm not going to really model specifically about the system. So I then kind of treat it as a black box, taking the controller, look at the outcome, and I want to see how this method is going to perform. Can I really guarantee certain stability, robustness, like some question about this? And the other hand, come back like the control for learning. Like if I really view this as a dynamical system, right? So what is that I can do? Can I help it? I even can show like the limitation for the original method. So let me dive into the details. So before the talk, the one common thing for these two parts is we're going to study the zeroth order method. So what the really zeroth order method is. So diving into a little bit of details here. So for the zeroth order optimization, you can also like is one of the black box optimization method. And here we do not know J, but there's one assumption we're actually making here is a J is differentiable. So the gradient is well defined, just there's no way to evaluate the gradient. So we do the black box feedback, taking the theta, getting the J theta feedback. So the gradient estimator. So zeroth order optimization roughly follow this line, taking the theta and then doing the gradient estimator based on the value J. You can imagine, okay, one easy way to do it to do the finite difference approximation. And the 2-point gradient estimator is kind of the finite difference approximation, just using less data point. At each time, rather than, so this dimension is a D, rather than to getting like the direction along the N direction, like just take a random direction. Once you take the random direction, do small perturbation, and then you can do the finite difference approximation. So look at here, if I making the gap is R, so over by R, this is kind of the gradient definition. Once if you're making the R going to be 0. So this is a 2-point gradient estimator, which is actually quite powerful. Like when people compare with the 2-point gradient estimator and the true gradient, the performance gap is quite small. But another the talk, actually, I'm going to focus on a different thing, the single-point gradient estimator. What's the reason behind? So what's a single-point gradient estimator? So rather than to do the finite difference approximation, just using 1 point of the value function, and then using this one can serve as a gradient estimation. So there are technical details, right? Why this is a gradient estimation? So I will refer to the paper. But I just want to highlight why, for the talk, I only focus on the single-point gradient estimator. As I mentioned, like this black box, it actually has a lot of uncertainty, like external disturbances, everything will come to play to shape what is the outcome is. So it's not really a like determinist case problem. So the finite difference problem under the like assumption, if my J and J theta plus perturbation is really the J, then it makes sense. But if my estimation J tilde is already corrupted by some external noise, the final difference, you can imagine, right? The final difference doesn't really make much sense. Because this is for different stochastic. This is for one realization, another realization. Why the realization really means the same thing, not necessary. So that's why people also like, wait, let's do just single point. So now like, hey, taking one, no matter what kind of environment is happening, okay, I have one information, at least this is a gradient for the current scenario. So that's where the single point estimator come from. And we're only going to focus on single point gradient estimator because we want to kind of use this method for the dynamical system control. So that's, as I mentioned, there's a very nice math theorem behind that, right? To guarantee this gradient estimator is kind of a stochastic gradient, but this stochastic gradient has bias. And the bias can be controlled by how large the perturbation will be perturbed. So this some preliminary of the zeroth order, like, and this for that two papers, you can find all the performance guarantee. So for the concrete things, first one, I will focus on a little bit more complex scenario. Like if I have multi-agent complex system, are we really going to use the zeroth method to helping us find the controller? And the other one, we should go back to talk about zeroth order method, right? Is this possible for me to improve it? Because you can imagine this one, look, if I can really implement, it's, as I mentioned, it works well. But single point, like it looks suspicious. It's really going to perform well, like only a single point would exactly the gradient information. So that's the motivation for this one. We actually want to improve the single point zeroth order method to see whether we actually can even getting closer to the 2-point gradient estimator. So like, feel free to ask me questions. So it's okay if I don't finish my talk, just want to making sure like I'm not really losing the audience from beginning. So now let's talk about first work. As I mentioned, as a control problem, we can treat it as a black box optimization problem. So let me put in a little more detail. We only focus on optimal control problem here, like not like some other control problem. So what optimal control problem means? So I have a dynamical system, observation, state, controller. So like first is this a stage cost be well defined at each stage t. So this t is the time like associated with the time revolution of the system. So once we put in the controller, right, if I just care about stage cost, which is not really enough, I really care about the accumulated cost. You can do the finite time horizon or you can do the infinite time horizon. So we're going to focus on the infinite time horizon. Like the two cases of infinite time horizon, you can do discounted, you can do the undiscounted. And once we have this cost, as I mentioned, we can view this as a optimization problem. So I parameterize my policy by some parameter theta. And then I treat this optimization problem. So like, but one condition for this control problem is that making sure my theta can at least making sure my system is stable before we really talking about optimality. So, and we're going to use those zeroth order method, right? Taking the theta, getting some realization, and taking the update, and to see how it works. And this update is the single point zeroth order estimation. So this is the like high level. And with this kind of view, like I said, there's a question, so I will talk about stability of optimality, confidence rate. So there are exciting positive news. So I guess some of you already even know this paper, it's 2018 by Mary Fazell group. So you look at this problem, like if I look at the standard, I first question, like, can this method even work for the standard textbook questions, which is the LQR, linear quadratic operator? Well, this problem is, right, my dynamics is linear, and I can have the full observation of the state. So I have a stage cost, which is quadratic, looks nice, because if I have this quadratic problem, I know the optimal controller is a linear controller. So I just need the parameterization of the K, right? Don't really need a like a fancy deep neural net to parameterize the controller policy. And once I have that, like if I have the model, I even can write down what exactly my JK is. So then I actually have a good understanding of the geometry of the JK, which probably helped me to analyze the system so that the convergence of the learning method. So like we treat this problem as a optimization problem. So as I mentioned, right, this is like in study 2018, once this paper being out, it's actually generating a lot of like excitement from both community. Hey, now it looks like the learning method can really like help in the control design this for this LQR problem. What do I mean? Like we do this, you can do the 2-point, single point, especially if I uncertainty do the single point. So by choosing those R, and also there's EDA, excuse me, like one typo here. Also the step size, be carefully. We can guarantee with high probability, the learning process is going to be stable. Like each K is going to stabilize the system as long as I start with a good controller K, like which is stabilized system. And then it's able to find the global optimal. So what's the reason, like why this is even doable? As I mentioned, is because this optimization method, it will relate to the optimization landscape. So even though the stable region is non-convex, but it's connected. And an additional nice property is the cost function JK here. As I, even it's non-convex, but it has this kind of nice property like gray domination. Gray domination is a kind of analogy of the strongly convex in the non-convex domain. So I can guarantee that the unique stationary point and this stationary point is the optimal point. Because it's got a nice property, everything works. So I'm not going to talk about details like how exactly this like NASA has been doing. I'm going to use this more complicated case to kind of raise some questions, right? So how we really guarantee those issues once we go to a more complex domain. So now let's dive into the problem I really want to talk about, like decentralized LQR. So this is motivated by those kind of societal network system I was talking about before. Like even that's assuming like I'm using the linear system to approximate the online physical dynamics. And I have the sensor actuator at different location. And although like, you can call those an agent or device I, he will observe some information of the system, but no one is able to really observe the full information immediately, right? It's only a partial observation. So, and then every controller like can take in their own controller, like the local controller to perturb the system. But like this is the local controller. So we focus on the control policy is I going to react to the local information observed. So once I put in this domain, the agent cost, again, everyone can observe how well the system is performing at this local location. If you think about thermal control in a complex building, right? For each room, you roughly know how good the temperature is, like how much is the most power you are really consuming. So this is kind of corresponding to those like local costs, right? Everyone observing how good the system is performing locally. And the objective is to find a good controller, like for every agent, for every device, to minimize the global cost, right? The global cost, I care about the entire system. For the transportation, I care about the congestion over the entire network. For the building thermal control, I kind of care about, hey, how well is the temperature around the entire building rather than just one room. So based on this domain, right, and here the difficulty question is a complex system. It's actually hard to model the A and the B. And on the other hand, A and B probably is also time varying since it's the approximation of some more complex dynamics. So the question we ask here is, can we use the local observation and local cost to find the optimal K? So how are we going to do it? Since as I mentioned, right, we kind of first want to see, can the zeroth order method be applied? So what the zeroth method looks like is going to, okay, take the controller, and this, remember the K controller here, everyone taking some perturbation and observing the outcome is the global system. And then we go ahead, right, what exactly each device should do? Each device should update their own K. So this is how they're going to update. And you can notice here, in order to update, I need to know how the global system is performed, which is a global cost. That's the first challenge, how the individual agent can get the global cost. And the other challenge is actually arising from the control stability point of view. So to perform this zero order optimization, I also kind of times my direction. This is like the perturbed direction. So for the perturbed direction, if I do the Gaussian, which is fine, everyone can take in their local Gaussian, the global K is still going to be Gaussian vector. But the challenge here is if I redo the Gaussian, my K means my controller can actually take a very, very large number, which is going to crush my system. So if I care about the stability at least with high probability, I need at least bounded my perturbation. So what this motivated us is even for the theory from the learning, I can do both Gaussian, I can do both like unit sphere random perturbation. But if I doing those control problem, it's better to stick to the unit sphere than the control, at least each time I try is at least bounded. But now there's a difficulty, right? So how are we going to really jointly random sample, like getting a sample from the unit sphere? I need some like coordination among all the agents. So putting two questions like, we need added communication, right? The only way to have some estimation of the global system, the only way to have some coordination, like probably through some communication, right? If agents allow to share some information with each other, like probably they have a way to estimate. The question is how we're going to estimate and how good the estimation is going to be. So the question for this problem is we're going to base on the local observation, local cost, local communication, and we would like to eventually find the optimal controller. And during the learning process, we want to guarantee stability and eventually we want to guarantee optimality of the case. So that's a question for the decentralized LQR. So let's see how the algorithm have been really designed. So as I mentioned, for those kind of problems, it's usually when we have a 2-time scale. So this is the 5-time scale is the real T from the dynamical system, like the same time scale at that for dynamics. And on the other hand, because this kind of black box optimization is I put in some controller, I observe the outcome. In order to observe the outcome, you need to wait for a certain time. So that requires the slow time scale. Each S we call like episode 1, episode 2. So how the algorithm performs, like first it's just outline. So we generate the random perturbation, like I'll tell you how we generate the add random perturbation later. And we can, like everyone apply the local control policy and they observe their own cost and they share information. And by sharing the information, they get in to estimate the global objective cost. Once they have some global estimation, everyone has their own local estimation of the global objective. They perform their zeroth order partial gradient estimator, and everything else is just following the zeroth order method, and then repeat the process. So let's dive in, right? How exactly they can really estimate the global cost. So the nice thing is here, global cost is just summation of everyone's cost. And for this problem, actually the averaging or consensus method can do a very good job. It's like each time for every agent, you have your own estimation, you have your own observation that you share with your neighbors, and you add what's really the new observation you're going to have. With the certain communication weight matrix being chosen, then the process is able to find the true global cost function. So, and this one, what's the performance guarantee, all those kind of consensus papers, you can grab anyone and to see what the performance guarantee can have. And it also has if we really run, weight the system run for TJ, that's how accurate it. So I want to highlight one thing, right? So this is a little bit, in my opinion, roughly different from the distributed optimization side. So even I don't have decentralized method, the centralized method I mentioned, I need to run my simulator, put in my controller, wait, and then update. So for my system, even for the single agent, I need to wait anyway. So for this problem, my multi-agent actually didn't really complicate my process much. You are waiting to understand your limit average of your cost. Then at the same time, you also exchange with the information. So we do not need to add another loop. All this kind of share information and estimate the global accumulated cost happen at the same time. So which is pretty nice. That's why we didn't really push in hey, if I really do the consent optimization, I will put in communication later on. But this is a natural way. I don't need to do that, right? Just kind of using the same inner loop process to also put in my estimation of the global cost. And now back to another one. So another thing, again, this is really because of stability. Once we put in the original algorithm, it looks okay if I make assumptions, but which is not really good when we really run those simulation for our problem, is because the J, depending how my stochastic has been going, my estimation, the C, can be very, very bad. And then my J will be really large in value, and making my J going to be very large, and then it actually crop my entire process. But the stochastic will ruin my system. So then the way to control it, we actually put in the upper threshold. Okay, we know this system, roughly I have I definitely need some initial knowledge. Roughly, initial knowledge don't need to be very accurate. So I put in some threshold, right? If it's really too large, this just doesn't make any sense. So we're just going to bound it, how much the global cost estimation we're going to have for the stability point of view. So this is about estimating the cost. The other one about the perturbation, as I mentioned, right? The perturbation, I need random, everyone, they need a jointly sample from the unit sphere. How are we going to sample it? This is a nice a fact, which actually is a fact. Based on this fact, the only thing they need to know, everyone can just do their own local sample, which is independent, and they just need to find a way to estimate the norm of it, which is the two norm of those vectors. And again, it's a summation. So what this means is I can use the same method I described before for the consensus or averaging to estimate the norm of the global J, global Z. And once we have this information, then we can just using the ZI over this norm, that is my random perturbation. And again, I want to mention that this process doesn't mean, hey, I need to have another inner loop. No. So all the sharing information, like how to jointly sample random perturbation, can happen concurrently with the process when we estimate the accumulated cost of J. So it's still the complexity is the same complexity as the single agent one, which is pretty nice. And now about the performance guarantee, you can probably already feel the most difficult part when we bring this learning method to the control is actually guarantee stability. Right, the probability guarantee is can borrow directly from the learning field, but for the stability, we did a lot of modification to making sure we actually can guarantee the closed loop system will be stable during the learning process. So we bound the perturbation, bound the estimator, and this additional thing why we actually can always be stable is the function structure is as a coercive structure. Means my gradient descent actually will drive my K, the controller, away from the unstable region. So now with this is stability, and then also I mentioned like the optimality. What about the optimality? So I want to come back to the discussion later, but what's roughly what we can guarantee is this. So sample complexity by this problem is 1 over epsilon force. So like there's some technical discussion we can have like after my talk is about, is this really optimal? So I do not have an answer for that, right? Is this the optimal sample complexity? And here by sample, we're really talking about at each t, the same time scale of the system itself. So it's the TJ is how many simulation steps we run for each episode, and the TG is how many episodes we have. Like in total, that's how much the sample complexity for this learning algorithm, right? Compared with the sample base, which one better, worse, and there any room for improvement? So like we can have this discussion like after the talk. But let me show you some simulation results. So to be honest, simulation result works better than what we would expected. So we simulated the building thermal control, like we simulated the simple one, also more complex one, also adding the external time varying outdoor temperature, which is not even not capturing our problem. And we look at the simulation, you can look at here, roughly just like by 100 iteration is kind of already making like the controller, making the system going to the right direction. And the iteration is corresponding to the episode that we're talking about before. It's actually faster than what our theory expected, but that typically is the case. The theoretical guarantee is always more conservative. But now let me come back to a more critical issue. So stability, like, yeah, we had a high probability. There's no additional definition of stability. But the optimality guarantee, this is kind of a little bit cheating here, is when we say optimality guarantee, but the truth is we only have the stationarity guarantee. It's like with how many samples, then my gradient will get small. So this is like, is this centering point really corresponding to optimal point? No, right? This is a weak optimality guarantee. So why we only have this one? So now that's like something I want to talk about, right? The importance of the geometry of this control problem. So now can come back to compare with the successful story we had before for the central LQ1. So for the central LQ1, we observe all the information X, and like we know this is the optimal controller. And the decentral LQ1, so for here, like, this is not really the optimal controller if we open up all the choice of classes of the controller. So we stick to this parameterization. It's Ki times my local observation. So if I stick, because my information is limited. So like stability, like we can guarantee them, but optimality. So for this type of research, if we really work hard, we can guarantee the JK will be smaller than the optimal K, like the JK star. But for this one, we also work very hard. That's the guarantee we have. And what's the reason of it? Now we look at the region. So for this region, even non-convex, but it's connected. It's just a one kinetic component. So if I start with some point, at least I have a hope to convert to the optimal point. So the central LQ problem, like this, actually done by Java's group, like it's actually can have a multiple kinetic component. So you can imagine for those kind of gradient descent, it's always kind of local improvement. Depending on my initial point, like it's hard to imagine how can you really jump. There's no way, like unless you're adding really big perturbation to your dynamics, there's no way, and it's hard to know which kinetic component is better. That's the first challenge we have. Like this local information dramatically making the problem way harder than the original one. And about the function structure, right? So now about the J, as I mentioned, this one happily surprisingly has so many nice properties. And like coercive, gradient domination, unique stationary point, happen to the optimal point. And then for the centralized, decentralized LQR problem, still one nice property is this, that's actually how we guarantee stability. So once I start like the gradient descent, we're making sure my system dynamics going away from the boundary region, that's called coercive here, but doesn't have any gradient domination. So that means the gradient really doesn't really mean much about your true cost function J. And then it's actually can have multiple stationary point. And basically we like, there's not much additional property to really say. So, but then that's putting one question, like, I think for you guys who took control class, well, say, okay, for those impression, it's not just a multiple agent. It's just because it's the bottom one, the more like challenging part is the partial observation, right? So the partial observation, that's kind of geometry for this structure, right? But then for us, and we took the control class, we know once we have the partial observation, like U equal KY, that's not really a good controller choice. The good controller choice should be dynamical controller. So like once I combine with the common filter and with my feedback control, that's actually my optimal controller for the partial observation system as for the linear system. So then we actually, like our group was interested for this question, right? Okay, so if I lift my parameterization to the dynamical controller. So rather than just 1K, now I'm actually have AK, BK, CK as my parameterization for my controller. But does this solving our problem? Like if this actually solving our problem, that would be nice. Then I can just, okay, for my decentralized LQR, rather than do the KX, I'm going to make everyone have a dynamical controller. So let's see like whether it really solve the problem, not solve the problem. So first of all, about the demand, I would say this is good news. Again, still it's non-convex, right? The stability always going to be non-convex notion once we do the parameterization. So, but there's one good news is it has the most two kinetic component once we lift up. So, and the two, you look at the image here, they're actually symmetric to each other. It's actually through the similarity transformation. So what does it mean is it doesn't matter. If I start my initial point starting here, I probably go to some point, and this one not going to lose any formality because the other component is just like a mirror of the other component. So this is great news. Like at least the gradient method is useful if I have this kinetic component. But unfortunately, in order to make this method work, I also need some problem with the JK. So the first challenge, once we really lift up, so they really lift up, you provide more like choices to actually go into the like unstable region. So it's not coercive. So the gradient descent, right? My cost function is kind of decreasing, but that doesn't mean my K is actually getting like stay in the compact set. It's actually getting like closer to the unboundary, unsafe, like unstable region. So which is really bad if I want to control the entire dynamics of it to guarantee stability. An additional thing, we actually like come up some kind of example to show definitely going to have multiple stationary point, and those stationary point they can be non-strict saddle point. What non-strict saddle point means is some of you are familiar with those machine learning study. People like for the stochastic gradient, if you add random perturbation, you can actually jumping out from the first order saddle point. Like that means that you Hessian has some direction for you to escape. But what is showing up here is we actually found some example. So it's both first order and also the Hessian is kind of zero, it degenerate. So which is really a bad news because you want to add a perturbation and it's probably still stuck at those non-strict saddle point like always. But there's another good news, and that's something we have been thinking like, can we translate like using this good news to think about what the good news says, even though it's kind of a different kind of station point. But if we check the station point, if we realize the minimal realization, what the minimal realization means is AKBK is controllable and AKCK is observable. So if the station point happen to be a minimal realization, then that point is actually going to be the global optimal. So at least one, like we had one way to check the quality of the solution. Like run the gradient descent is, if it's kind of converged stuck at some point, you can check the point. Hey, if it's minimal realization, if it is, then it's global optimal. But the difficulty here is when we were, based on this property, can we just like parameterize my controller as a minimal realization? Like I can do the AKBK being controllable canonical form, AKCK be those observable canonical form, then that is going to help. So we haven't really had much progress in that yet, because once you do another parameterization, like you say the controller or the minimal realization parameterization, then it's actually changing the additional geometry. It's different. So in summary, like you say, like I put in an example to say it's useful and to a certain degree for especially even if you go ahead dealing with a nonlinear complex system. So those zeroth order model free method is useful because typically just so hard to really find some solution. But then it definitely also has a lot of challenges, and how good the algorithm going to perform, it really will depending on the optimization landscape of the underlying problem. So like with that, going to roughly conclude my first part. We can have more discussion afterwards. So any question? You want to ask question now or as I'm going to talk? Then I will continue to talk about second part, the control for learning, which is a little bit different flavor compared to this work. But the motivation is actually, again, come back to we actually want to improve in those masters, then I can do better control. So come back to this performance guarantee, right? I kind of mentioned one thing here is the sample complexity we put in is this is sample complexity. And we were trying to ask a question like, if we do the sample-based masters through those kind of zeroth order optimization, is this the optimal things we can do? Can remove those like complexity, not really 1 over epsilon 4, so it's doing something better. So that's something we ask ourselves, right? Can we do better sample complexity? So I think lots of you will have the question, hey, like you just doing like the zeroth order method I was showing there is just the Vernina gradient descent. How about doing the X-rated gradient descent? So yes, we're going to accelerating the zeroth order optimization, but I'm not going to talk about Nastro. So I will have one slide for Nastro to say the problem for Nastro when we really use Nastro for this type of problem. So we're going to accelerating the zeroth order optimization, but how we're going to do it? We're actually going to come back to the traditional control and the electrical engineering perspective. So let me take a detour to tell you a similar story, right? Zeroth order optimization, I think a lot discrete time, a lot of learning and optimization people have been working on it. But in the control field, we have something similar, which is almost exactly the same, like which took me a while to eventually know this actually called extremely seeking control. I don't know why, but like this is called extremely seeking control and similar to the zeroth order method. So what this extremely seeking control is, it's quite powerful and very similar, right? It's rather than think about the discrete time, this is a continuous time dynamics. And like if I do the gradient flow, do the gradient, this is my gradient. But the problem, as I mentioned, right, I don't know the f, so there's no way for me to evaluate the gradient. Only function evaluation is available. So how the extremely seeking control people have been doing? So this is the block diagram for extremely seeking control. So typically, every time when I was a student or I'm a professor, so when I teach control, actually I will feel headache when I see a block diagram, which is too many arrows there. But for this case, I'm going to show you the block diagram is actually very helpful, especially to explain where the method comes from. So I'm going to go the block diagram step by step to explain it. So here, this is the gradient flow, but I don't have the G information. Right, so I will take this, like you can call this is the state of decision X. So what's the extremely seeking have been doing is add some perturbation. The perturbation is a small probing signal and control and E like sinusoid, right? You know the sinusoid you can generate by those RC circuit, IOC circuit. So now you add this perturbation. So rather than using the F, right? So I'm going to do the perturbation. This is the outcome I have. And what the G is? The G is going to be this information times the small perturbation signal. That's my G. Putting them together. So that's like sometimes I found this headache of the block diagram because you want to understand the block diagram, I still don't know what's really going on. Okay, what's really going on is actually pretty simple, just one line. It's a x dot equal minus k. This is the f times sine. So now you look at I will have a slide to compare with the zeroth order, right? This is my function realization. This is my perturbation direction. You can generate into the multiple dimension, just like here, the sign is going to be a vector of different sign, so a signal. So, but the perspective difference. So for this one, right, how people analyzing this is to do the averaging. So roughly this method will approximate the gradient flow in the continuous time. To show a little more intuition or visualization, what exactly the method been doing. So the frequency, typically you're going to put in very large frequency to perturb, and your A is going to be small. Like you don't want to crop your original signal. So this is the trajectory of the X you will see. So it's have a like time scale separation. So for the fast time scale, this is the fast variation due to those perturbation. And then this is the slow variation that's actually describe overall how the X is being evolving, which is the gradient flow, the true gradient flow. So how people analyzing it is like for this function, as we kind of one assumption, assume it's kind of differentiable. And actually here, even like I'm using the Taylor expansion to explain it. So from the Taylor expansion, that's how it looks like. The fx plus this is perturbation. So from control and dynamical system area, how people analyzing it is to do averaging. So I average the dynamics over time period, like especially if you put it into the period of the standard signal, then this part will kind of canceled once you do the integration. You only got one for this part, and this is a small error since coming. So from the extremely seeking control, like it looks similar to the zeroth order method, like the method, the analysis method definitely different. But now let me compare why I say that it looks identical to me. Right, the only difference, now you can compare together. So continuous time, discrete time, not really big difference in this one. So now perturbation, this is a deterministic signal, sinusoid. This is a random signal. And magnitude, like I would still need to control how much I'm going to perturb. And I'm going to control how much I'm going to perturb. So the R and the control gain is like how aggressive my controller, like my system dynamics react to the signal, okay? And the step size, right? So you see like almost you can find all those analogy, like one by one correspondence between the two methods. Since I can find one by one, now I'm actually going to come back to the block diagram. As I mentioned, like for me, I think this block diagram is actually helpful for me to think about improving the method. So block diagram for the single point estimator. Now this is my single point estimator. I need a gradient estimation. So how it's been doing, right? My current X, add a perturbation. There's a problem signal, putting this problem signal in and observe outcome. Observe outcome, and then this is my gradient estimation, multiplication. It's almost the same thing, like just replace the correspondence in this block diagram. By doing this way, we know the zeros author method behave this one. And for here, we do the expectation. The expectation is will roughly perform as a gradient descent. So why I want to do the block diagram? Now come back to extreme sigma control. So when we look at the extreme sigma control textbook, so we found, hey, like because people actually use extreme sigma control in practical physical system. Then people observe, okay, something we don't like, we want to improve it. So how people improve it? Like here, I'm going to show people actually add filters into it. So what the filter is? So here had a high pass filter, had a low pass filter. So for the low pass filter, when I first seen it, I thought it makes sense, right? So like the too many noise, fluctuation going on, I want to add in some low pass filter to get in the true gradient information. That's kind of my hello intuition. But then like high pass filter, like it's already too many noise, too many fluctuation. Why you actually need the high pass filter here? So now this is, so why people need it? So for the high pass filter, it's actually going to wash out some DC component, which is not useful for my gradient estimation. I will show you even more math later on to tell you why the high pass filter is actually a very good thing here. And the low pass filter, indeed, is kind of like wash out some high frequencies to get a better gradient estimation. So like in the control textbook, distributed control textbook, you actually can find this, like the high pass filter, low pass filter, well improving the transient behavior. So you will have less oscillation, you have much smoother transient behavior before you really convert to those output point. And you can imagine, like, I bring the block diagram. Now since I have block diagram for, okay, before that, give a little more intuition about how these filters work in the extreme DC control. As I mentioned, like, so one tricky thing, like why the high pass filter work? The high pass filter, so at this part, the signal is this FA x plus A is sine omega t. You do the time expansion. So now I can actually see what are the two components. So Fx is a slow frequency, almost like the DC component, and this has a frequency. So the high pass filter is kind of only keep the high frequency part. So now what it's going to do is it will keep, like, this is the roughly my gradient estimation. It's going to be 2 sine square, and this actually cosine square part. So, and you do this, this is the F gradient. And once I do the low pass filter, it's actually remove this high frequency part. You're actually almost getting the exact gradient information. So the two filter here really helping me to getting better accurate, like better estimation of the gradient. So now we're putting into the discrete time, like our single point zeros order method, what we're going to have. And now, so first I will tell you the result. We're putting them in, and it worked. And actually it has a different, like we can have a different intuition explanation, like what exactly is kind of high pass filter and low pass filter. So for the high pass filter, what it's been doing is actually introducing a residual feedback. Rather than just using, still it's a single point. Each time do the one perturbation, you're getting your current estimation of the like F cost function. And this is the previous time, right? It's still a single point, but I'm not really throwing away my original point. So if the function is smooth, then what is kind of natural implication for the high pass filter is actually going to use some residual feedback from the previous time. That's the high pass filter part. And the low pass filter is actually corresponding to the momentum method. But this is different from natural, as I will show you later. The natural method, well, like if you not really do carefully with the momentum, it will cause the trouble. So this is like the low pass filter will introduce a momentum to this dynamics through a certain way. Together, that helps the dynamics. I can give you some flavor how we really get it. It's pretty straightforward. High pass filter, continuous time, we just do the discretization. So when we do the discretization, we find the discretization, then it's naturally discretization will introducing the residual feedback. This is a high pass filter. And for the high pass filter, as I mentioned, the residual feedback is, so they actually a paper happened like 2020, they actually like find through another way to add the residual feedback, they realize that it can help the single point zero order method. And this actually, we have even a broader class of method. You actually can really talk about how this kind of filter, how strong you really want, you actually can shape your dynamics. So this is the high pass filter part. And the low pass filter, similarly, do the discretization, you put in those information there, roughly look at the discrete time, how it look like. So some math we did is like, rather than just putting the two block diagram, we can put in the diagram together, and that can give us more intuition what exactly the low pass filter have been doing. It's actually adding this momentum term. And again, it also tells us like once we really change the hyperparameter, what those hyperparameter corresponding to. So putting together, as I mentioned, right, so you see, I put into the block diagram, which helped me to find the analogy and know like which part that I can change and improve it. we come up with a new single point zeros order method. And like the two component, the high pass filter roughly can explain the sense that it reduces the variance. And the moment it kind of do some acceleration for this method, but different from the natural acceleration. And the performance metric, as I put in here, this is the table. This is the Vanina single point zero order method, and this is the residual feedback, which means they only had a one particular high pass filter in the single point estimator. And this is our method with both high pass and low pass filter. And this is the benchmark, the 2 point, because so I would like to clarify one thing, the 2 point, like if at scenario, if I really just do the optimization problem, I have the function f here available. The 2 point estimator is definitely better than single point because you have finite difference approximation. It's at a much smaller variance, has much smaller values. So the 2 point is kind of our benchmark we want to compare. So you can look at the simulation result, like indeed, our high low pass filter almost achieved the like similar performance of the 2 point, but there's still a gap because the 2 point have additional sample information. In summary, like for the second part, I already kind of show you how this traditional electron engineering tools for diagram can help us to rethink those learning methods. And you can actually, like another way you actually can go ahead to play with, so rather than the first order high pass filter, first order low pass filter, probably you can even go ahead with like even more complicated filters, and that's probably generating different kind of dynamics, and which one is better, which one is worse. That will be interesting research direction in the future. And so as I promised, I will show you something, the negative result of natural. So the natural, this is a continuous time of the natural method. So we actually study this dynamics and we realize this method is not robust. So for this natural, like this is a very simple method, strongly convex function. We just add noise into the gradient estimation, it becomes unstable. So the way how we actually making the method be robust, like this is critical because I mentioned, right, there's no way to, like all the problem we have been doing, so the gradient is not going to be accurate. You do the single point estimation or you do the stochastic gradient estimation. This is never going to be accurate. It also has additional error, but the natural method will blow up the entire like learning process. So we actually can do some like robustifying these methods through different tools. The tool we did is we do the hybrid regularization. Is after a while, we actually regularize this additional t here. So we just can do some restarting, which is kind of similar. The learning community also realized if you restart the T, it probably can improve the system dynamics. And for us, we actually can really putting them into the formal hybrid system to study the phenomenon, to really control it and look at the dynamics much cleaner. So with that, I would like to conclude my talk. Hopefully, like today's talk is just some like beginning or give you some inspiration if you're interested in the topic about interplay between control and learning. And I'm actually teaching a class, learning interplay between learning and control this semester. So since you guys are at MIT, feel free to stop by. And I'm looking for TF for my class. I still don't have any TF for my class. So thank you.
Thank you, Professor Lee, for the wonderful talk. So if you have any question to ask, please just raise your hand or type your question in the chat box. So, okay, so I guess I can get started. So I'm wondering, it's like, so is it possible to, in the second part of the talk, is it possible to apply some more sophisticated or more advanced filters into the optimization method? And is it possible that they will have even better performance?
So I don't have a specific answer for that. So we can tell you something what we tried. So we only studied the first order filter. For the first order filter, for the residual feedback, we did some study for the beta choice. So it turns out the beta equal 1 is actually can give us the best numerical result. But the theoretical result cannot really show that. Like so far for the table we have here is kind of limited by the technical tool we have. And once you go with more complex domain, my answer will be this, depending on the problem, right? Depending on the structure of the F, right? Whether your higher order of the filter will help or not help, that's well depending on what kind of F we are really dealing with. Yeah, thank you.
Thank you. And Professor Illich.
Hi, Mariam.
Hi, Lena. Can you hear me?
Yes, yes.
Yeah, so very nice talk. I have a pretty basic question. When you do the identification, yes, how do you know that you have sufficient excitation to recover the physical process?
So like, first of all, like for the talk I've been doing here, I didn't talk about the model-based method, system identification. And then regarding the question you have, right, for system identification, if I go to learn the model, and it's a study, we actually have some recent paper, but still have some assumptions we'll start with, right? So given how many samples, like if it's a linear system, then we actually have a theorem to say how good the estimation will be. But that's under knowledge. I know roughly the model order, like if it's the 10th state, then it's 10th state. That's the information we need. But for that one, we have some. But in general, I put the question. In general, if I even don't know what the online, how many orders of the system.
But we already have examples in application that you sort of miss something that's a physical disturbance when you are doing the identification. And from there on, it's down the hill. So maybe we should follow up.
Yes, that'd be great. That would be great. Yeah. We actually have very nice like progress on simplification. Even you have the nonlinear feedback control, but the system is linear. Then we have a statistical guarantee about how good estimation can be.
Right.
That'd be great.
I think very important actually. I'd like to talk about that. Yeah. Thank you.
Great. Thank you, Maria.
Due to time limit, we're only able to take the last question, and that comes from the chat. So Shinjaku asks, where can I find more information on the class, like the course number?
Okay, I can type the course number here. So it's ES203 or AM233. Has the two titles.
Thank
Are
you.
you looking for the TF? I need a TF. Okay. Actually, to be honest, there's already too many students, but I would like a very good teaching fellows.
Okay. So due to time limit, our plenary talk just ends here. Let us thank for Professor Lee's wonderful talk again. Thank you so much.
Thank you, everyone. And feel free to email me. We are very close. Thank you.
So, and now we will be having a coffee break, and the student session for the control and game theory will begin in about 10 minutes, starting at 10:15. See you then.